Welcome, my geniuses. Welcome to another part of our excitable physiology playlist. We'll be talking about membrane potential. Under membrane potential, we'll talk about the action potential and the resting membrane potential. So these are the two potential, but we'll cut the video into two. We'll do resting membrane potential and we'll do action potential because we need them throughout the course of our excitable physiology playlist. So make sure you stick with us to the end. So if you are a newcomer, you are just joining us, make sure to subscribe and turn on your post notification button so that anytime I drop any video, be sure to be notified. So let us move right into the video. So for the beginning, now let us just talk about the brief introduction to membrane potential. So the first question we'll be asking ourselves, what is membrane potential? Now the membrane potential is a result of neurons moving in and out of the cell. Are you getting me now? Through the membranes. Because neurons enter into the cell and neurons move out of the cell. Are you getting me now? So the result of this polarity of neurons going in and out of the cell is called what? Membrane potential. But if the membrane potential occurs when neurons are moving in and out of the cell to facilitate resting of the membrane, you call it resting membrane potential. But if movement of neurons facilitates the membrane should be active, you call it what? Action potential. So the word action will tell you, the word resting will tell you. So resting membrane means I am facilitating neuronal input into the neuron to facilitate the membrane should be at rest. Now if I am facilitating the membrane to be active, I call it what? Action potential. So easy. And the membrane we'll talk about it under general physiology. So the membrane, we'll call it cell membrane or we'll call it neurolemma. So we have the cell membrane and we have the cytoplasm and we have the nucleus under our general physiology. So but here we're just talking at for the membrane should be porous for in and out of neurons, call it membrane potential. And to do this, it must be dependent on three factors. Are you getting me? To do this, it has to be dependent on that three factors. Are you getting me? Mnemonic CAP, CAP. Are you getting me now? So the first one we're talking about is the concentration of the ion in and outside the cell, in and out of the cell. So there are some ions that are more dominant outside the cell and there are some ions that are dominant inside the cell. Are you getting me now? So we'll talk about sodium Na+, talk about calcium, talk about magnesium. Most of the ions are present outside the cell, or even chlorine are in the ECF. So ECF means extracellular fluid. So these neurons are present more outside the cell than inside the cell. The one that are not present inside is potassium. Potassium is more inside the cell. Proteins are more inside the cell. Are you getting me now? So these are, now you have to know their concentration outside and inside the cell. 2A means that you have to talk about the activity of the electron pump. Now what are the electron pump? So when you are pumping out something, you need energy, and once you need energy, so if you are pumping something from the area of what lower concentration to area of higher concentration, take for instance, you want to pump something from inside the cell. Now if something like sodium is present outside the cell and not inside the cell, it is much more outside the cell. So if sodium is inside the cell and you want to pump sodium out from inside to outside, you need energy because it is more outside. So pumping it from area of lower to area of higher, you need energy. So example is sodium potassium ATPase, because potassium is good inside the cell, it is more better inside the cell. So if you pump it from area of lower concentration, which is outside the cell, to area of concentration inside the cell, you call it what? You need sodium potassium ATPase. And also calcium too. Calcium also need a transport pump to pump it inside or outside the cell. The next one is permeability of the cell membrane to this ion. So there are some ions that are not freely able to move in and outside the cell. So you check about 1, their concentration of the neuron inside and outside the cell, 2, activity of the pump, and 3, the permeability of the cell membrane to this neuron, CAP. Now in picking the first one, I'll talk about the resting membrane potential. Are you getting me? Now the resting membrane potential, now this you also see the potential difference inside and outside the cell when the membrane is at rest. So if I am facilitating the movement of ions inside and outside the cell to facilitate resting, I call it resting membrane potential. So one thing you have to know that the inside of the cell is negative. Ions inside the cell are relatively negative except from potassium. Potassium is positive ion but it's present inside the cell. Are you getting me now? But inside the cell is always negative, while outside the cell is always positive. So there are some negative ions you can see outside. Are you getting me? Which is chlorine. Chlorine is Cl minus, so it's outside the cell. So we all know the idea is that inside the cell is much more negative, which gives us the negative sign we see. So the resting membrane potential of every tissue is from minus 9 millivolt to minus 100 millivolt. So that minus is showing that, okay, inside the cell they have what? Negative ion. Amino acids, they are also negative ion. Are you getting me now? So many of them, they are all negative ion. They are present inside the cell, while those outside are positive ion. So the resting membrane potential we move from minus 9 millivolt in the graph, minus 9 millivolt to minus 100 millivolt. Are you getting me now? So the minus doesn't mean, are you getting me now? The minus doesn't mean, so you cannot compare minus 90 millivolt to minus 80. So you think that minus 90 millivolt is what? Smaller than minus 80, based on, you know, that the one with the the one with the highest minus is much more lower with the one with the lowest minus. It's not like that. Minus is just showing that they are in the resting zone. It doesn't mean that minus 90 is much more lower than minus 80. No, minus 90 is much more higher based on value, not on the negative. Are you getting me now? So that's what I've explained. One, negativity is much more inside the cell than outside the cell. So if negativity is much more inside the cell, which accounts for the minus. Do you get it now? So are you understanding? So you talk about the resting membrane potential, the movement of neurons to facilitate the membrane should be at rest, and much more because the ions inside the cell, or the substance or solute inside the cell, are usually negative, which accounts for the negative value of the ions. Are you getting me? The next is the measuring of the resting membrane potential. To measure the resting membrane potential, you have to use an intercellular recording method. So that intercellular recording method is that I'm using 2 microelectrodes. That 2 microelectrodes, one is used to penetrate the cell. Now that one I'm putting inside the cell, I'm calling a recording electrodes. Are you getting me now? Why the one position outside the cell is called the reference electrode? That if I use these two and connect it to a voltmeter, are you getting me now, and use a battery, what will happen? I'll be seeing the impulses. See, I'm recording inside the cell. So if I'm completing this circuit, I close on the switch, what happens? As impulses is moving to the voltmeter down to the active electrode, which is the recording electrode inside, what will I be seeing? I'll be seeing what is happening inside, which will be minus off in my voltmeter. Are you getting me now? So as the current is going from the positive to the negative, what happens as it is moving around, I'll be seeing how negative the value will be. Why? Because I put the active electrode inside the cell, which will record negative value. Do you understand? So since you have known, the reference electrode is outside the cell, while the active electrode or recording electrode is inside the cell. So if I on the switch, as it is moving inside, coming outside, moving inside, coming outside, you'll be seeing the value in the voltmeter will be negative. So the next is the ionic basis of resting membrane potential. What is the ion? The next is the ionic basis of resting membrane potential. So what is the ionic movement to the cell membrane? One thing you have to know, that the resting membrane potential is generated in the cell membrane. So which means we want to look at how the ions move and in and out, and which ions are much more favorable when they are moving in and out. So I can always repeat to you, I tell you that there are much more anions, which is negative ions, inside the cell than outside the cell. So there are much more positive ions which are in the extracellular, and there are much more anions intercellularly. So since you have understood this, now at rest, what happens? You see that it is much more like the membrane is much more permeable to what? Potassium K plus. The potassium is much more permeable to it. So potassium can freely move at resting membrane potential. So when the cell is at rest, it's much more easier. The ionic gate will open for potassium to leave. But now it is moderate to sodium. Sodium can only enter lessly because we want the cell to be at rest. Why it is impermeable to what? Large intercellular anions like proteins. So proteins are inside the cell, which means they cannot diffuse out. This unequal permeability to ion creates that concentration gradient across the cell membrane, and this concentration gradient, that's what resting membrane potential is built. You get it now? So for your exam question 1, inside of the cell it contains more anions, outside of the cell contain more cations. Again, based on ratio, based on grades of permeability, potassium is much more permeable than sodium, and the lastly is impermeable to large intercellular molecules called proteins. Are you getting me? And due to this inequality, that is where we can now explain what resting membrane potential is. Now at rest, what happens? Like I said, the potassium leaves. We do not want what we want inside is negative, we don't want positive. So potassium, that is the only positive inside, leaves to the exterior, which means it diffuses out, is efflux outside to the extracellular fluid, like outside the cell, leaving in much more negative ion. So if we are living in much more negative ion, this creates that what resting. Are you getting now? Because for activity to occur, there must be depolarization. And what is causing depolarization? Positive ion flowing into the cell. Are you getting? So if potassium is inside the cell, it doesn't mean that the cell is always 100% at rest. But to make it go to the resting membrane potential, potassium must leave, leaving negative charge what proteins that are inside the cell. This leads to the separation of charges across the membrane, and therefore the potential difference across the membrane. So now if I want to look at it experimentally, now what happens? Potassium efflux can be what? Blocked by applying what? Negative charge ions to the inside part of the cell. So if I want to what? Block potassium from leaving, what happens? I have to create much more negative ions inside the cell. So if I'm putting much more negative ions inside the cell, that was the goal of doing of a resting membrane potential. That's the goal, to create much more negative inside. So if I create much more negative, potassium do not have any reason to leave. Are you getting now? Because at that particular point is much more balanced. So one thing you have to know, that the negative charge across the membrane that is necessary to oppose the movement of potassium, naturally potassium must leave. Are you getting now? So if I increase the electronegativity inside the cell, it will oppose the potassium from leaving. I call this what? Equilibrium potential of what? Potassium. Equilibrium potential of potassium, or we call the E substitute K, is the what? Amount of electronegatively charged molecules you can apply inside the cell in order to oppose potassium from moving to be effluxed outside the cell. Are you getting now? So naturally, since we know potassium can leave, if I now create a much more electronic negatively charged inside the cell, it will prevent potassium to go outside. Now what will happen now? This will keep what we call equilibrium. Potassium will not move outside. Are you getting? This fact that we have explained now for the equilibrium potential for potassium has showed us that potassium has the highest advantage to live outside the cell. Like it is much more what? Permeable to go outside the cell. Are you getting now? This is very simple. Now the movement of these ions that we have talked about through the what? Cell membrane is what? By simple diffusion. Are you getting now? It's by simple diffusion. Naturally, in our general physiology, we did what? Transport across membrane. Transport across cell membrane is by passive and active diffusion. Are you getting that? Passive and active diffusion. In passive diffusion, which takes simple diffusion and facilitated diffusion. Now, this movement of this ion is just by simple diffusion from a region of higher concentration to a region of lower concentration. No energy is required. But now to maintain the concentration gradient across the membrane, we use what? Active transport. But this one we just explain now, the movement of potassium. So potassium must be let go outside the cell in order to leave electronegativity molecule like protein inside the cell to allow the cell to rest. And in order to show that experimentally that potassium is permeable, what we have to do is to apply more electronegativity inside the cell to oppose potassium from going outside the cell, which we call equilibrium potential for potassium. You get him now? To maintain the concentration gradient across this membrane, I tell you we use active transport. And in using active transport, what happens? We are going to use ATP if we are using active transport. So what will happen? Now remember, potassium is outside, sodium is already inside. Are you getting? Like I said, when the cell is permeable, what happens? It allows moderately sodium to enter. Sodium is outside the cell, potassium is inside the cell. So naturally, if potassium is permeable going outside the cell, sodium is eventually going inside the cell. So if sodium is already inside the cell, potassium is outside the cell, what will happen? To make it to go back to its normal concentration gradient, what happens? I'm using ATP. What ATP? I'm using what? Sodium potassium ATPase. Like 3 sodium, 3 Na, 2 potassium ATPase activity or pump. So if I'm using 3 sodium, 2 potassium ATPase pump, which means I want to drive out all sodium outside the cell and bring potassium inside the cell. So 3 sodiums, 3 amount of sodium is being exchanged for 2 amount of potassium going. So sodium is going outside, potassium is coming inside the cell. So this activity we have just done creates a deficient of potassium charge inside the cell. So if we are driving all the whole sodium that is positive from that is already inside the cell, drive it outside the cell, what happens is to create a deficient of what? Positive charge inside the cell. Are you getting me now? Thus creating an additional negativity of minus 4 millivolt. Because remember, we said the resting membrane potential we are using is minus 90. So if now for it to be minus 90, which means there will be amount of sodium that is inside the cell. So if I create or drive out all the sodium outside, I'll create a negative value inside of the electronegativity to be minus 4 millivolt. Are you getting me? So now the simple diffusion for sodium, that enter the cell is about minus 86 millivolt, while the one that for sodium that are left outside the cell creates a minus 4 millivolt. So know it, sodium that went outside by 3, I use 3 sodium, 2 potassium ATPase activity, which means I'm driving sodium outside and potassium inside. So if I'm driving sodium outside, I create a net negativity of minus 4 millivolt, while the simple diffusion of that I've created that took out all the potassium outside the cell initially is about minus 86 millivolt. Are you getting me now? So if I'm to create the combined interaction between simple diffusion and what active transport will give us a resting membrane potential of minus 90 millivolt. Minus 4 millivolt created by sodium being pumped out, and minus 86 millivolt created when potassium went out initially during resting membrane potential, creating a total of minus 90 millivolt in nerves, skeletal and cardiac muscle. Are you getting now? So simple diffusion is the battery that drives resting membrane potential. Are you getting now? So why active transport act as a battery charger? Very simple, you are seeing there. So the resting membrane potential works more on simple diffusion. Are you getting now? Why? To bring it back to its normal way, to bring it back to its normal concentration gradient, I use ATP, which is sodium potassium ATPase activity. So I hope it made sense to you and you have understood all I've explained now about resting membrane potential. So I try to explain this part to you very well so that you understand it. So I don't want to rush, I don't want to do anything, I just want you to understand it. So next to be going into is action potential. Are you getting me now? So stick with us to the last. If you are just new, make sure to subscribe, turn on your post notification button so that anytime I drop any video, be sure to be notified. So bye bye, see you in my next video.